Welcome friends, Igor is here, and in this video we will learn how to compute eigenvalues and eigenvectors. In this lesson we will discover that the eigenvalues of a square matrix can be computed as roots of its characteristic polynomial. The eigenvectors of a matrix can be computed as non-zero elements of a null space of a certain matrix. And we will define and compute algebraic and geometric multiplicities of eigenvalues. Let's get started. We begin the process by computing eigenvalues of a matrix. Once we compute eigenvalues of a matrix, then we will find eigenvectors which correspond to every eigenvalue. Suppose that A is a square matrix of size n, then a scalar lambda is an eigenvalue of the matrix A if and only if it is possible to find a non-zero vector x such that matrix vector product AX is equal to the scalar multiple of the vector x by the given scalar lambda. This is simply the definition of an eigenvalue of a matrix. But now, the equation AX equals lambda x holds if and only if the following equation holds. We can replace the scalar multiple of a vector x by the scalar lambda with the matrix vector product, where the matrix is the identity matrix scaled by the scalar lambda. Please check that multiplying vector x by this matrix is the same as simply scaling the vector by lambda. We then use properties of matrix product, namely its distributive property, and we rewrite this equation as follows. But now we see that the equation AX equals lambda x is equivalent to saying that the vector x belongs to the null space of the matrix A minus lambda I. Lambda is an eigenvalue of the matrix A if and only if this equation has a non-zero solution vector x. In other words, lambda is an eigenvalue of A if and only if the null space of the matrix A minus lambda I contains a non-zero vector. But to say that the null space of a square matrix contains a non-zero vector is the same as to say this matrix is singular. Also, in one of the previous videos we have proved that a square matrix is singular if and only if its determinant is equal to 0. Therefore, lambda is an eigenvalue of the matrix A as long as the determinant of the matrix A minus lambda I is equal to 0. So, to find eigenvalues of a matrix A, we need to find scalars lambda such that the determinant of the matrix A minus lambda I is equal to 0. We are going to give this determinant a name. Let's say A is a square matrix of size n, then the characteristic polynomial of this matrix is defined as the determinant of the matrix A minus xi. This is a polynomial in the variable x. With this new terminology, our previous criterion can now be rephrased as follows. The eigenvalues of a square matrix A are precisely the roots of its characteristic polynomial. Let's consider an example. We have this 3x3 matrix F and we are going to find its eigenvalues. The first step is to find the characteristic polynomial of the matrix F, which is the determinant of the matrix F minus x times identity matrix. This matrix is obtained from the matrix F by subtracting x from each entry on the main diagonal. Then we use a variety of techniques we learned in the previous videos to compute this determinant, and it will turn out to be a polynomial of degree 3 in terms of x. We also factor this polynomial so that we can easily see the roots of this polynomial. It follows that matrix F has two eigenvalues, 3 and -1. Once we established the eigenvalues of a matrix, we will look for the eigenvectors which correspond to each of the eigenvalues. One caveat is that each eigenvalue has infinitely many eigenvectors which correspond to this eigenvalue. Suppose we have a square matrix A and lambda is one of its eigenvalues. Then the eigenspace of the matrix A for the eigenvalue lambda is the set of all eigenvectors of the matrix A corresponding to the eigenvalue lambda plus the zero vector. Recall that the zero vector cannot be an eigenvector, so we artificially add this zero vector to the collection of eigenvectors. The reason for this will become very clear soon. Let's observe that the eigenspace of a matrix A corresponding to an eigenvalue lambda is in fact the null space of the matrix A minus lambda I. First observation, the vector x belongs to the eigenspace if and only if Ax equals lambda x. This is not as trivial as you might think, so let me explain this equivalence. There are two types of vectors in the eigenspace. They're either eigenvectors or the zero vector, which is never an eigenvector. So if x is an eigenvector with the eigenvalue lambda, then certainly it satisfies the equation Ax equals lambda x. However, if x is the zero vector, then it also satisfies this equation. Then we're simply going to transform this equation, recalling that we can think of a scalar multiple of the vector x by the scalar lambda as a matrix vector product. We then use the distributive property of matrix multiplication, and the last equation says exactly that the vector x is an element of the null space of the coefficient matrix of this linear system. Therefore, the eigenspace of the matrix A corresponding to the eigenvalue lambda as a set is equal to the null space of the matrix A minus lambda I. Why? Because they have identical elements, and element x belongs to the eigenspace if and only if it belongs to the null space. Now, this tells us that the eigenspace is actually a subspace. That's why we call it eigenspace rather than eigenset. And now you see the reason why we had to add the zero vector to the definition of the eigenspace, because if it did not contain the zero vector, it would not have been a subspace. The proof of this is trivial. We just showed that the eigenspace is the null space of some matrix, and we proved previously that every null space is a subspace. See, this is the power of mathematical abstraction and generalization. But still, it might be useful to see an explicit proof of this fact to have a better understanding of how eigenvalues and eigenvectors work. So here's an alternative explicit proof which checks all subspace conditions. First, is this subset non-empty? Yes, sure. By the definition, the zero vector belongs to every eigenspace. Is it closed under vector addition? Let's take two arbitrary vectors, x and y, in this set. Then we're going to look at the matrix vector product, matrix A, multiplied by the vector x plus y. We use the distributive property of matrix multiplication, and then we use the assumption that x and y come from the eigenspace. Finally, we use the property of vector operations, and this computation shows that the matrix vector product of the matrix A and the vector x plus y is the scalar multiple of the vector x plus y by the scalar lambda. Does this mean that the vector x plus y is an eigenvector of the matrix A with the eigenvalue lambda? Actually, no. Do you see why? The problem is that the vector x plus y could be the zero vector. But if x plus y is the zero vector, then it is an element of the eigenspace by definition. If x plus y is not the zero vector, then the above computation shows that it is an eigenvector, and therefore it is a member of the eigenspace. You see how careful you have to be when you work with the eigenvectors. You always have to check that the vector you get is not the zero vector to call it the eigenvector. Finally, third part, we need to show that this is closed under scalar multiplication. So let's take any scalar alpha and any vector x from the eigenspace. Then we look at the matrix vector product, matrix A, and the vector alpha x. Using properties of matrix multiplication, we can move the scalar in front of the product. By the properties of vector operations, we can switch lambda and alpha, and this computation shows that matrix vector product of matrix A and vector alpha x is a scalar multiple of the vector alpha x by the scalar lambda. Does it mean that the vector alpha x is an eigenvector of the matrix A with the eigenvalue lambda? I hope by now you're careful enough to recognize that not necessarily. If it is the zero vector, well, then it is a member of the eigenspace by the definition, and if it's not the zero vector, then yes, it is an eigenvector of A corresponding to the eigenvalue lambda. But this completes our three-step check, and this is an explicit proof of the fact that the eigenspace is always a subspace of the vector space of column vectors. Now, let's go back to the problem of computing the eigenvectors of a matrix. We already figured out that this matrix has two eigenvalues, 3 and -1. Next, we are going to take one eigenvalue at a time, and we are going to compute the eigenspace corresponding to this eigenvalue. But the eigenspace is just a null space, and we know how to compute null spaces. So let's take first eigenvalue 3. We construct the matrix F minus 3 times identity matrix, and to compute the null space of this matrix, we find the reduced row echelon form of this matrix. We see that there is one free variable in the solution to the corresponding homogeneous linear system, and therefore the null space of this matrix is spanned by one single vector. You may want to check out this video to recall how to find the basis of the null space. Observe that this eigenspace has dimension 1. Next, we consider the second eigenvalue, -1. We construct a matrix F minus -1 times the identity matrix, and we find the reduced row echelon form of this matrix. There are two free variables in the solution to the corresponding homogeneous linear system, and therefore the null space of this matrix has a basis which consists of two vectors. This means the dimension of this eigenspace is equal to 2. So let me summarize the whole process. We start with a square matrix, and we would like to find its eigenvalues and eigenvectors. Step 1, we find eigenvalues of the matrix as roots of the characteristic polynomial of the matrix. Step 2, we take one eigenvalue at a time, and we compute the corresponding eigenspace as the null space. For each eigenvalue, you have to compute a separate eigenspace. Let's define the notions of algebraic and geometric multiplicities of eigenvalues, which will be useful for us later on. The algebraic multiplicity of an eigenvalue is the highest power of the term x minus lambda that divides the characteristic polynomial of the matrix. In other words, it is the multiplicity of the corresponding root of the characteristic polynomial. Each eigenvalue is a root of the characteristic polynomial, and therefore it is divisible by at least one copy of x minus lambda. This means the algebraic multiplicity of each eigenvalue is a positive integer. The geometric multiplicity of an eigenvalue is the dimension of the corresponding eigenspace. Each eigenvalue comes with at least one non-zero eigenvector, therefore each eigenspace is a non-trivial space, so its dimension is at least 1. Therefore the geometric multiplicity of each eigenvalue is also a positive integer. Going back to our example, let's compute the algebraic and geometric multiplicities of each eigenvalue. For the algebraic multiplicities, we look at the characteristic polynomial. The algebraic multiplicity of the eigenvalue 3 is equal to 1. This is because the factor x minus 3 appears with power 1 in the characteristic polynomial. And the geometric multiplicity of this eigenvalue is also 1, because the dimension of the eigenspace corresponding to this eigenvalue is equal to 1. For the eigenvalue -1, the algebraic multiplicity is equal to 2, because the term x minus -1 comes with the square in the factorization of the characteristic polynomial. And the geometric multiplicity of this eigenvalue is also equal to 2, because there are exactly two vectors in the basis for the eigenspace. So, in this example, the algebraic multiplicity of each eigenvalue was the same as the geometric multiplicity. Is it always going to be the case? As we will soon discover now. If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will find connections of eigenvalues and eigenvectors with properties of linear independence and non-singularity. I will see you later.